Hello, everyone, and welcome back. So, we're picking up right where we left off in our chapter, Is Matter Around Us Pure? In our last session, we spent a good amount of time on mixtures. Today, we're going to look at the other side of the story, pure substances. We'll find out what exactly elements and compounds are, and we'll also learn how to tell the difference between a physical change and a chemical change. Ready? Let's begin. So, here's our plan for today. We'll start with a quick recap on what a pure substance is, just to refresh our memory. Then we'll dive deep into elements and compounds. After that, we'll figure out physical versus chemical changes, see how everything we've learned fits together, and finally, we'll try a few questions to see how much we've understood. All right, let's get started. First things first, a very important recap. What do we mean when we say the word pure in science? Now, I want you to think about this for a second. You go to the store and you see packets that say pure milk or pure ghee. For a common person, that just means there's no adulteration, right? But for a scientist, does pure mean the same thing? The answer is actually no. You see, here's the scientific meaning. For a scientist, a pure substance is made up of only one single type of particle. Every single particle in it is chemically identical. That's why milk is actually a mixture, It has water, fats, proteins, different particles. But something like sugar, where every tiny particle is a sugar molecule, that is a pure substance. So now that we're clear on that, let's talk about the first type of pure substance. These are the absolute basics, the fundamental building blocks of all matter. We call them elements. An element is the simplest form of matter you can get. Think of it like a single Lego brick. You can't break it down any further using any chemical reaction, like heating it or adding something to it. An element like, say, iron, is as simple as it gets. It's just iron. Now, elements can be broadly classified into three types. First, we have metals. You see them everywhere. They usually have a shine, which we call luster. They are malleable, which means you can hammer them into thin sheets, like aluminum foil in your kitchen. They are also ductile, meaning they can be drawn into thin wires, just like the copper wires used for electricity. And of course, they are very good conductors of both heat and electricity. The second type is nonmetals. And well, they are pretty much the opposite of metals. They don't have that shine, you can't shape them into sheets or wires, and they are poor conductors. Simple examples are all around us. The oxygen we breathe, the hydrogen gas, or carbon, like in a piece of coal. All very important nonmetals. And then, there's a really interesting group right in the middle. These are the metalloids. They show some properties of metals and some of nonmetals. The most famous example is silicon. It's not just some element on a chart, it's the heart of our modern world. All the chips inside our phones and computers are made from silicon. So, we have our building blocks, the elements. But what happens when these blocks start to combine with each other? Well, that's when they form our second type of pure substance, compounds. Now, there are two phrases on this slide that are absolutely crucial. Chemically combined and fixed proportion. This isn't like just mixing things in a bowl. A chemical reaction has to happen that actually joins the elements together, and they always join in the exact same ratio. Let's take water, H2O. It always has 2 hydrogen atoms for every 1 oxygen atom. Every single time. That proportion is fixed. And this is the most amazing part about a compound. When elements combine chemically, they totally lose their individual properties and form something brand new. Just think about this. Hydrogen is a gas that can burn with a pop sound. Oxygen is a gas that supports burning. But when these two combine chemically, they form water, H2O, which we use to put out fires. The properties are completely different. Isn't that fascinating? This classic experiment from your textbook shows the difference perfectly. Imagine 2 groups. Both start with the same things, iron filings and sulfur powder. Group I just mixes them together in a dish. That's it. But Group 2 mixes them and then heats the mixture strongly, forcing a chemical reaction to happen. Now, just look at the results. In Group I's mixture, the iron is still iron. So if you bring a magnet close, the iron filings will stick to it. But in Group 2, where they heated it, something new was formed. This new substance, iron sulfide, is not attracted to a magnet at all. And look, when you add acid, the mixture gives off hydrogen gas, which is a property of iron. The compound, however, gives off hydrogen sulfide gas, which has that smell of rotten eggs. See? A completely new substance with totally new properties. This experiment leads us to a very important question. How can we be sure if a new substance has actually been formed? The key is to understand the difference between physical changes and chemical changes. It's quite simple, really. A physical change just changes the appearance or state of a substance, but not its chemical identity. For example, when ice melts, it becomes liquid water. But both ice and water are chemically H2O. Nothing new is formed. But a chemical change creates a completely new substance. When you burn a piece of paper, you're left with ash and smoke. You can't get the original paper back. That's a chemical change. Let's try to classify a few examples. Cutting of trees, well, you just have smaller pieces of wood, so that's physical. Rusting of an almirah, that's chemical. Iron is reacting with oxygen to form iron oxide or rust, which is a new substance. Boiling water is physical, just a change from liquid to gas. Now, dissolving salt in water, this one can be tricky, but it's physical, because if you evaporate the water, you get the salt back, right? And what about burning a candle? Well, here, both changes are happening. The wax melting is a physical change, but the wick burning to give heat and light, that's a chemical change. Okay, we have covered quite a bit. Now it's time to zoom out and see how all these concepts, mixtures, elements, compounds, all of it fits together into one big picture. This will help you organize everything in your mind. See how it all connects? At the very top, we have matter. All matter can be divided into two main categories, pure substances and mixtures. We just learned today that pure substances can either be elements, which are the simplest form, or compounds, which are elements that are chemically combined. And from our previous class, you'll remember that mixtures can be homogeneous, like salt solution, or heterogeneous, like muddy water. This is the complete classification for the chapter. Fantastic. Now that we have the full map in our minds, let's put our knowledge to the test. I'm going to give you a couple of questions. My suggestion would be to pause for a moment, try to answer them yourself, and then listen to my explanation. Okay, let's go through this list. For sodium and silver, are they on the periodic table? Yes, so they are elements. What about soil and air? Are they made of many different things just physically mixed? Yes. Soil has sand, clay, minerals. Air has nitrogen, oxygen, other gases. So they are mixtures. Now, calcium carbonate, does it have a fixed chemical formula, CaCO3? Yes, so it's a compound. And finally, sugar solution, it's just sugar mixed in water. You can get the sugar back by evaporation. So it is a mixture. And for our last question, which of these are chemical changes? Let's look at the options. Freezing of water is just a physical change from liquid to solid. But what about the others? Growth of a plant is a very complex series of chemical reactions called photosynthesis. Rusting of iron, as we discussed, forms a new substance, iron oxide. And cooking of food, you are definitely causing chemical changes that create new substances with new tastes and smells. So A, B, and C are all chemical changes. Keep revising these core ideas and you will have mastered this chapter. All the best!